so now we're into inputs to the PLC. And what I've done here is I have all these blocks that show inputs and so forth. And this shows you that this is kind of a wiring diagram detail, because these blocks are these blocks. And in fact, these are disconnectable, okay? And this says 1C, and here we have 1C, 0, 1, 2, 3. So our diagram is broken up by the connectors on the PLC, right? Which makes it easy to understand. You're looking at that, you can go right here and see there's the same nomenclature, and this is all the inputs. Now, you'll notice that we have plus 24 and we have minus 24, and the minus 24 comes around and goes to the other side here and hooks to all of these inputs. So what are these inputs? A limit switch for home on the tailstock, left tool post home, right tool post home, length sensor. So these sensors are all connected to the minus side. Why? Well, this is what's called a syncing input. There are two kinds of inputs, syncing and sourcing. The difference is that on a syncing input, we take plus 24 to the module's common, right, the 1C, and then these out inputs, they all pull the signal down to 0, okay? Now, why? Well, when transistors were first invented, they didn't have transistors that could pull up, they only had pull down. So it became really common to have this kind of thing. Now, this is the opposite of what you see in AC. In AC, your switches and all, everything is, you have grounds, or you have the common, the neutral, and those are not syncing, those are sourcing. So in AC power, it's all sourcing, but in DC it can be syncing or sourcing. I've stayed with syncing only because for a really long time, way more sensors were available as syncing than there was for sourcing. If you were using sourcing, you frequently had trouble finding a sensor that worked with sourcing. So this is the convention.
So we have both syncing and sourcing PLCs here, just because that's what we end up with right now.
Yeah, because of supply issues.
Because of supply issues. So each time we switch between those two types, we have to switch sensor types as well.
Yep, that's why. Now, some sensors, quite a few sensors are both sync and source, right? But yes, that becomes the issue if you have a bunch of sensors that you sync and you go syncing to source. That's why you want to stay with one or the other, right? Now, how does it change? Well, if this was a sourcing input, this fuse would feed this side, and the common would go to the ground. And that's how you can tell that inputs are syncing and sourcing, by looking at the schematic. If the common is a plus, then it's a syncing. If it's a minus, then it's a sourcing. So that's how we wind up with this thing. Now, the terminals and the nomenclature here, none of that changes with sync and source. Pretty much the only way to tell on the PLC is by the part number. There's a different part number. One digit on the PLC is different, right? But because physically the PLCs are all identical that way. All right. So now you notice we have two different devices here. These are what they would call dry contact. That's, in other words, just a switch, physical switch. All right. So we have 3 physical switches for the home sensors. But then we have one here that says prox switch. Well, prox switch, there's multiple kinds, but in our case, the prox switches are what they call inductive proxes. And what they are is they generate a magnetic field that senses metal. So this sensor is looking at a piece of metal, and and can judge when the metal is in the field, all right? Proc switches are very useful when you have things moving, and you can get them with different ranges, so you can have something that doesn't have to be real close, or you can have ones that are quite close. Now in the case of these guys up here, these physical limit switches, they're like 5 microns position, okay? And this down here, plus or minus a millimeter or 2 or more, depending on what switch we choose, okay? Then we get over here on, you see this ASG1 and 2. These are actually output contacts from the servos themselves. And so what this is their nomenclature is all systems go. So what this is an input to the PLC saying that the servo successfully moved where you told it to. So we look at that all the time as we're moving, and we make a move and we look at the ASG to see, did the move complete? And are we actually where we told it to go? So that's the feedback from the servos to ensure that we're actually there. Because if you're not there, well, the next stage could be a crash. You know, something else could move, and you told it this part to move, and it didn't move, so that would be bad. So that's where that comes in. So then we have another, you notice we have one called left tool post collision. Well, that's because in this case we have multiple things running on the same track, and so there's some possibility they could come together and collide. And so that input just is an extra safety over and above the ASG to make sure that if we have a problem, we can sense it. We can say, well, you know, I'm not supposed to be right up against that one. So that'll stop the motion and keep us from doing damage. All right, let's go further. Okay, so you can see we have a whole bunch of more sensors, right? We have another collision sensor, and then we have photo eyes, and the PE just stands for photo eye, right? And we have magnetic limits. These are proxies also, but they're magnetic. They sense a magnetic piston in the stop unit, right? And so we have in-feed stop up and down, and grippers open and close, and you know, all these sensors, they all go into the PLC inputs. Now, one of the things you cannot tell from this wiring diagram, and this is something that's kind of newer, since the advent of the PLC, the schematic can't really tell you how the machine works, because there's no information here about the program, right? In other words, all this data gets collected, but there's no indication in the schematic as to how the machine actually functions. So in order to know how the machine functions nowadays, you actually have to have the PLC program to look at, and when we get to that, you'll see that the PLC program looks very much like this wiring diagram. It's why they call it ladder logic. It was designed when they started replacing relays with PLCs. They made the programming software kind of look the same. So it's easy to, if you understand this, you understand the other, right? So all of these numbers are the actual inputs on the PLC, right? So let's go up again. All right, so we just have some more digital inputs. Then we have some analog stuff. So analog inputs are inputs that are not on/off, they are a number. And in the case of the PLCs we're using, they are programmable for what the inputs are. They can be 4 to 20 milliamps, or they can be 0 to 20 milliamps, and they also can be voltage, plus or minus 10, plus or minus 5, 0 to 10, and various things depending on the programming. But the key factor is that these can bring in a number, a value from, say, an air pressure sensor, Okay, so we can monitor the air pressure, which is critical if you're using the air for things like the grippers. If there's not enough air, the grippers might not close properly. And then we have, if we have the lasers on here where we're measuring diameter, we would get that as an analog input. So they put out a number. Now in our case, most of the time, we are using 4 to 20 milliamps and not voltage. The reason for 4 to 20 milliamps rather than voltage is that it's more noise resistant, and you can tell if you have a failure. If you're using 0 to 10 and you have 0, it indicates that nothing's happening. If you're using 4 to 20 and you have 0, it indicates there's a problem. Anything less than 4 milliamps is a problem. So that's why the 4 to 20 is more reliable that way. If you get a broken wire, 4 to 20, it tells you right away, oh, there's a broken wire. I have to have current all the time. And there's other good reasons for that. But so anyway, so all the connector, all the analog stuff comes in and gives us numbers that we can work with. All right, let's go further. Okay, so now what we have is we're now into outputs. And if you notice up here, if you come up here a little bit, from servo control supply, the numbers now starts is 219 and 218, and that's because it's coming off of the servo power supply, not the other one. So when you're working within the panel, you have to be aware that there's more than one power supply, all right, or source. They are not the same source, but they have different wire numbers. That's how you keep it straight when you're looking through the panel. Go ahead.
So the 219 originated on sheet 2, right? That's where that
Yes.
number got its number, and now it's showing up here, and now we're on sheet 7, I guess, because of the 700 digits, right?
Yes.
Does that mean the physical wire in the cabinet is going to have 2 labels on it, one that starts at 219 on one end and it ends at 700?
No. There's a contact missing here.
Oh, okay.
And that's where it changed.
Okay.
As I said, this is an out-of-date drawing, and the contact
it's
is
in
there.
progress.
Well, good
Yeah.
question. I was wondering that myself.
Well,
I thought there was a contact or something.
Well, do you ever have a teacher that actually makes a mistake on the board just to generate a question?
No, we've never had one.